next week classes will not be there. Shown by phenols only. Nitration. This is something you should know because these type of reactions we have talked about in 11th grade as well. The nitration by electrophilic aromatic substitution with dilute nitric acid at low temperature, phenol yields a mixture of ortho and para nitrophenols. So phenol with dilute nitric acid, ortho and para. Para is the major one. Nitration. The ortho and para isomers can be separated by steam distillation. These have significantly different, or at least you can say sufficiently different boiling points. So these can be separated by steam distillation. Orthonitrophenol is steam volatile due to intramolecular hydrogen bonding, while paranitrophenol is less volatile due to intermolecular hydrogen bonding. In case of ortho, there is hydrogen bonding within the hydrogen and nitrogen within the molecule. So these molecules are not attached strongly with other molecules. So suppose you have this one molecule, another molecule, force of attraction is less. But in case of paranitrophenol, it is rare possibility that there will be hydrogen bonding between these two because these are far away. But there is great possibility that OH of other molecule comes closer. So there is hydrogen bonding in case of para amongst the molecules. So this is called intermolecular. When it is within the molecule, then it is known as intramolecular. So just to compare it with real life scenario, if there is any competition, sports competition in various schools, okay, so various schools are competing with one another, then it is called inter-school competition. When different states in India, for example, the teams of different state compete, it is known as inter-state competition. But suppose the competition is within a school, the teams of different houses or clubs within the school, then it will be called intra-school competition within the school. Same convention here. Within the molecule, intramolecular. Different molecules, intermolecular. So this is the reason here hydrogen bonding will be within the molecules. So two molecules will not be attached with great force. So that's why low boiling point. So it is steam volatile. But here it is difficult to remove these two molecules from each other because they are hydrogen bonded. So not so volatile. Not steam volatile. So that's why these can be separated. Simple question appears from here. You will write two lines and this diagram, everything here, what is written. Yeah. These two lines you will write and this diagram will be the answer. With concentrated nitric acid, phenol is converted to 2,4,6 trinitrophenol. Remember the previous reaction was with the dilute nitric acid. Okay. Now going back, dilute nitric acid. With dilute nitric acid, ortho and para isomers, two compounds will be obtained. If it is concentrated nitric acid, you will get picric acid. Although the yield of picric acid in this case is very low, we don't get picric acid in very good amount. Okay. So this 2,4,6 trinitrophenol is commonly known as picric acid. This method is not very good method. It has very low yield or poor yield. of picric acid. But in conversion, you can use it very frequently. There is no restriction if this appears in conversion. And normally you will see we will be using this method and the more efficient method, which I am going to show you just in few seconds. Just write down these. Make sure that during the class you are writing all the reactions. It will help you to memorize. If you write afterwards, it will require more time and you will not be able to retain. During the class, if you write it, it will help you to retain the reactions in your mind. One important point here, that 2,4,6 trinitrophenol is known as picric acid. Normally you will get written as picric acid, so you must remember it is 2,4,6 trinitrophenol. Nowadays picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it into phenol 2,4-disulfonic acid, then with concentrated nitric acid. Remember, we are still reacting it with concentrated nitric acid. The second step is still concentrated nitric acid, but the first step is concentrated sulfuric acid. That's the difference. So first we get it reacted with concentrated. This is concentrated, so write it. And we get 2,4-disulfonic acid because it is phenol. So we say phenol 2,4-disulfonic acid. And then we get it reacted with concentrated HNO3. Same compound we get. But in this case, yield is very high. The replacement of sulfonic groups by nitro group is easier, much easier as compared to attachment of nitro groups on the benzene ring. Write down this reaction. Some very good named reactions we will be talking about today. And if you just make sure that you remember those reactions, it will be easier for you to sail through very easily through the organic chemistry. Halogenation, it is similar, okay, similar to nitration. On treating phenol with bromine, different reaction products are formed under different experimental conditions. If conditions are different, okay, and this is very important one. CSCl3 or CS2 and at low temperature, monobromophenols are formed. I said the products are similar, conditions are different, okay. So here you will get ortho and para as you got in case of nitration. The conditions you must remember. Bromine in carbon disulfide at very low temperature, 0 degrees Celsius, 273 K. The usual halogenation of benzene takes place in presence of alloyous acids such as FeBr3. Here we are talking about phenol. Shashwat, that's why we don't use it. Okay, so that's why if you see here, it was written that nowadays picric acid is prepared by this method. In case of phenol, the polarization of bromine molecule takes place even in the absence of Lewis acid. It is due to highly activating effect of OH group attached to the benzene ring. 1 mark question appears from here. And what is the question? Question is about these two statements. The usual halogenation of benzene, if it is benzene, it takes place in presence of Lewis acid, such as FeBr3. Why? Because it actually polarizes the halogen molecule. That's why. But in case of phenol, there is already OH group. So OH group is already activating group. We don't need the FeBr3, etc. Lewis acid means we don't need Lewis acid in case of phenol. And this is the answer. In case of phenol, we don't need Lewis acid because OH group attached to the benzene ring is highly activating. So there is no need of Lewis acid. When phenol is treated with bromine water, 2,4,6 tribromophenol is formed as white precipitate. It is important that you remember, very important reactions I am talking about, okay? It is similar to that one. 2,4,6 tribromophenol is similar to 2,4,6 trinitrophenol, okay? So there also we got similar products. Here also we are getting similar products, only conditions are different. And one very important point which will help you to identify the compounds, that it is actually white precipitate. So when it is treated with bromine water, phenol is treated with bromine water, we get 2,4,6 tribromophenol and it is white precipitate. Try to repeat it in your mind 2-3 times so that you retain it. All these points will be used to answer the questions. So don't think that you will do it later on. Now the question. Write the structure of the major products expected from the following reaction. Mononitration of 3-methyl phenol. Mononitration of 3-methyl phenol. Can you tell me? Mononitration, you remember for mononitration, what were the conditions? Okay. Major product wise, Ashi. Now here two products will be formed first of all. Okay. Two products will be formed, out of which one is the major product? Or if both are major product? Think about it before I tell you. You remember that mononitration, I am going back, or let me explain here only. If mononitration is done, then there are two possibilities, ortho and para. So it will be done by the same dilute HNO3. Remember, with concentrated HNO3, picric acid will be produced or similar compound. Okay. Here, picric acid will not be produced because CH3 is already there. So ortho and para will be produced. Okay. So when ortho is produced, you need to understand where the NO2 group will get attached. It is like this. There is possibility that ortho position is this one, ortho position is this one also. So there is a possibility that ortho can get attached here, but not. Because here you have hindrance, more hindrance from this side due to these two groups. But from this side, you don't have that much hindrance. So what should happen? It should get attached at that side where there is less hindrance, not here. So ortho position, NO2 group will get attached to that position which has less hindrance. Then para position is para position, there is no confusion there. It is just opposite to OH group. Two compounds will be produced, and in this case, who will answer whether both are major products, whether any one is major product, and which one? Yes, it was due to steric hindrance, correct, Ashi. Okay, para one will be major one because at para there will be accent test. But having said that, ortho one will also be not in very less quantity. The reason is that if you consider ortho and para at both positions, you have similar hindrance. This position has hindrance from this OH group, and this NO2 group has hindrance from the CH3 group. There will be slightly higher hindrance rather at para position because CH3 group is larger than OH group. So both will be produced as major product. It is about steric hindrance, which is similar. Next question. Write the structures of the major products expected from the following reaction. Dinitration of 3-methyl phenol. It will be dinitration because methyl is already at meta position, so it will block something, but dinitration of 3-methyl phenol. I'm just showing it. Okay. Due to hindrance, you won't have NO2 here. So NO2 will not be here due to hindrance because at meta position CH3 is there. NO2 will get attached here. Now, who will tell me for dinitration? Actually, it was trinitration. 2,4,6 trinitrophenol, you remember, was done by what reagent? What you used for trinitration, which is actually dinitration here. Good, Shashwat Ashi. Both correct. Divya correct. Be active. If you want to score very good marks, be active during the class. Remember, if you can answer correctly here, you will never forget it. Rarely any chance you will forget it. Okay. Mehak, yes, very good. Okay. So both answers are correct. Whether you say only concentrated HNO3 or as Mehak said, concentrated H2SO4 and then concentrated HNO3, both answers are correct. Yes, Vanna. Concentrated HNO3 is the right answer, or concentrated H2SO4 followed by concentrated HNO3. You, in this case, due to hindrance, NO2 will not be there. That's why you will get dinitro. Next question. Write the structure of major product again for mononitration of phenyl methanoate. Phenyl methanoate. Anyway, I'm just showing it. Now, first, you need to consider phenyl methanoate. Phenyl means just benzene ring attached to something else. And methanoate means CH3COH. So it is simply you have phenyl methanoate. This is phenyl methanoate. So just nitration. And in this case, this group is very large group. So both these ortho positions are aesthetically hindered. So major product in this case will be that NO2 group will get attached at para position only. So major product will be para only in this case. Remember in previous cases I said both. Here it will be para only. Yes, Ashi, correct observation. This is phenyl methanoate. It is also written as just, COOCH3. Esters are written like ROCOR dash or RCOOR. Basically, you can consider that if it is acid, it will be RCOOH. If it is ester, this hydrogen is replaced by another alkyl group, which is written as ROCOR. So normally this is the way you will find instead of this this one normally you will find it written like this. Now very important reaction, coal-base reaction by electrophilic aromatic substitution. Remember we are talking about only those reactions which are shown by phenols only, not by alcohols. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive. You remember we talked about phenol gets reacted with NaOH and it gets converted to phenoxide ion. Okay. You remember that? Now tell me what other compound or anything else we can use, we will get the same product. Substituent here. Instead of NaOH, what we can use, we will get the same product. Deveno, Ashias. Reactions of phenols. We have already talked about this reaction at least, this part. That is when you get it reacted with sodium. Whether you get phenol reacted with NaOH or you get it reacted with sodium, both will give you phenoxide ion. So this phenoxide ion, okay, is actually more reactive. So I'm writing it more reactive. Remember, it is more reactive towards electrophilic aromatic substitution. More reactive towards electrophilic substitution. Yes, Ashi, correct. In case of NaOH, H2O is obtained. In case of sodium, hydrogen is obtained. Correct. Phenoxide ion, phenoxide is same. Hence, it undergoes electrophilic substitution with carbon dioxide, which is a weak electrophile. So this is the reaction. Phenol reacts with NaOH, forms phenoxide ion. Phenoxide ion is more reactive towards electrophilic substitution, and with even carbon dioxide, it gives us OH group, COH group with OH group. And this is compound known as salicylic acid. Many questions will appear from here. Salicylic acid, 2-hydroxybenzoic acid. Acid has higher preference. Acid group has higher preference. That's why it will be benzoic acid. When it is benzoic acid, this one is 1, this will be 2. At second position, we have hydroxy group, 2-hydroxy, which is known as salicylic acid. Now, similar to this one, if it is instead of acid, it is CHO group, that will be salicylaldehyde. So both are very important about salicylaldehyde. Also, we will be talking about both reactions are very, very important. So remember what named reaction I am talking about? I am talking about coal-base reaction. One of the very important reactions invariably appears or alternate day or even successive years. whether it is asked as named reaction or asked as, you know, what happens when, or asked that what will happen if this is treated with this one. Okay. Next one is Reamer time and reaction. Again, very important one. And here it is CHO group. So on treating phenol with chloroform in presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring. This reaction is known as Reamer-Timon reaction. So if you see, it is very much similar. You have phenol. From phenol, you get salicylic. Instead of salicylic acid, you get salicylic. Instead of COOH group, now you have CHO group. You can skip writing this intermediate. Okay, this portion can be skipped at all. Okay, entirely. Now understand the difference. Okay, the difference is in always reaction, carbon is introduced by carbon dioxide, and that is the second step. The carbon of COOH is introduced by carbon dioxide, and this happens in second step. First step is just NaOH, which gives you phenoxide, sodium phenoxide. In case of Reamer-Timon reaction, where you get salicylic, the reaction is different. That in first case, apart from NaOH, you use CHCl3 also, and that introduces carbon in first step. So here you use, along with NaOH, you use CHCl3, and that introduces the carbon of aldehyde group. After that, when you get reacted with acid, you get OH group. So steps are slightly different, but end products are very much similar. So just memorize it. You can convert phenol to salicylic. You can convert phenol to salicylic acid. If you convert it to salicylic acid, it is Kolbe's reaction. If you convert phenol to salicylic, it is Reamer-Timon reaction. Repeat it in your mind 2 times. You convert phenol to salicylic acid, Kolbe's reaction. You convert phenol to salicylic, Reamer-Timon reaction. Shashwat, by NaCl, can it be Na attached to oxygen and HCl formed? Shashwat, there are many possibilities. This is one of the possibilities what you have written, right? Here we are talking about specifically what is called Reamer-Timon reaction. So that's why specific to that one, we will use those reagents only. Yes, it is electrophilic substitution, Vanna. Okay. So we are talking about in both cases, always electrophilic substitution, and here also electrophilic substitution. Next is reaction of phenol with zinc dust. This is basically the uh, very good conversion, very simple conversion when you want to convert the phenol to benzene. So phenol to benzene conversion, you will remember it is just reaction with zinc dust. All these conversions you must memorize right away. I am planning to schedule a Viva just after the summer break week. So make sure that you remember, memorize all these reactions. What are the reactants? What are the reagents used there? Which one is major product? What is the name of the reaction? Then oxidation. Remember, I am talking about the reactions which are shown by phenols only. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone. Diketone benzoquinone with chromic acid. All these things are important. Chromic acid, benzoquinone, you should remember these are interrelated. They have some link. Means phenol when reacted with chromic acid gives us benzoquinone. In the presence of air, phenols are slowly oxidized to dark colored mixtures containing quinones. This is benzoquinone, diketone, right? You see diketone, it has two ketonic groups. That's why it is called diketone. Write down the reaction, very important one, and memorize right now. After some time, I may ask you to repeat any reaction. Okay. Now, in this case, now here I have written Na2. I have not written chromic acid. I have written, you know, sodium dichromate and H2SO4. These actually give us the chromic acid. So these produce chromic acid, which is used. Is chromic acid. Now the question: give structures of the products you would expect when alcohols butanol and 2-methylbutanol separately react with HCl, zinc chloride, and HBr and SOCl2. Means there are 6 reactions you have to write. First, you will write reaction of alcohol butanol with all three and reaction of 2-methylbutanol with all three. So A part is actually reaction with butanol, reaction with 2-methylbutanol, and so on. Now this one is Lucas reagent. And you remember that Lucas reagent with primary alcohol, secondary alcohol, tertiary alcohol, the conditions are slightly different, but it is primary alcohol given butanol. Okay. So primary alcohols do not react appreciably with Lucas reagent at room temperature, hence no reaction will take place. Tertiary alcohols will react immediately. Secondary alcohols in 5 minutes. Primary, no. Then 2-methylbutanol. 2-methylbutanol here is 3-degree carbon. The carbon which is attached to alcoholic group is attached to 3 carbons. 1, 2, 3. It means it is 3-degree. Tertiary alcohol. Tertiary alcohol will react. This OH will get converted to halogen group. Here in this case, HCl means chlorine. So it will give turbidity very quickly. This is actually a test for different types of alcohols, tertiary, secondary, primary. So you will be using this test, Lucas test, to identify or separate 1 degree, 2 degree, 3 degree alcohols. Um, no Arohi, no. Okay. Then with HBr, HBr's reaction with butanol and 2-methyl butan 2. This one, when HBr reacts, OH group will get replaced by bromine. Simply. Yes. One bromo butane. And when 2-methyl butan 2 3 degree reacts with HBr, again OH will get replaced by bromine. This one is easy. Next one is reaction with SOCl2. SOCl2, you know, is a reagent which is used to convert alcohols to halides. That is actually very good preparation method because both of the other products produced are gaseous, HCl and the steam. That's why, sorry, HCl and SO2. That's why it is preferred method. So when you get butan one all reacted with SOCl2, these are gases both, and you get halide. Similarly, in case of tertiary alcohols also, same, you will get halide and SO2 and HCl. So B and C part easy, but first part you need to remember that is actually Lucas test. And HCl plus zinc chloride is known as Lucas reagent. Next question. Predict the major product of acid catalyzed dehydration of 1-methyl cyclohexanol. Write it in your notebook. Everyone should have notebook. Write it there. Acid catalyzed dehydration. I told you the mechanism of this one, and I said that this is very important mechanism. It is asked as it is. Acid catalyzed dehydration. 1-methyl cyclohexanol. Tell me the major product in chat window. First, draw the structure of 1-methyl cyclohexanol and then see what will happen if OH from this carbon and hydrogen from the other carbon is removed. Dehydration. Okay. Dehydration means OH and H will go away. But just think about it. What should be the product and what will be the product? Okay. Ashi, correct answer. So dehydration means this OH will go away and H will go away from the adjacent carbon. Adjacent carbon means either this one or this one. So whether you have double bond here or here, it is same product. Hydrogen goes from here. Remember, these all are CH2 in cyclo. These are all CH2, not written here. So one hydrogen will go away. These two will form 2O. When OH and H will go away, the remaining electron will form double bond here. One methyl cyclohexene will be the major product. Keep writing all these reactions. Second one, the major product of acid catalyzed dehydration of butan 1 all. So again, dehydration, OH goes and H goes. Now, why? This question is rather very important and appears very frequently. Okay, so you will think that normally CH3, CH2, 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 OH, when it will lose OH, so it will lose OH from here and hydrogen from here. So it can be CH, H. I am writing CH2 as CH and H. H from here. So double bond should appear here. So I am writing it should. What will happen, we will talk about later on. I am first writing what should. So it should look like this. Double bond should appear here. But what actually happens that it is due to the mechanism that secondary carbocation is more stable than primary. And if there is a possibility, I'm repeating, if there is a possibility due to very less energy requirement that the hydrogen can move from one carbon to another carbon and it can be converted from primary carbocation to secondary carbocation, then this may happen. And this is the case where it happens. What actually happens that when CH3, CH2, 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 OH, in this case, what happens that when carbocation is formed, so first this carbocation is formed, CH2, CH2, CH2 plus. Okay. But the secondary carbocation is more stable than primary. So this actually gets converted into secondary carbocation and hydrogen moves from this one to this. Hydrogen moves to terminal carbon and the next carbon gains positive charge and it is more stable because it is 2 degrees. Why it happens? It happens because in this case, the transition of hydrogen from one carbon to another carbon requires very little energy. That's why. And then further reaction takes place. So that's why double bond appears here. That is written here. So a mixture of but1-ene and but2-ene is obtained. Why? Because there is transition from primary carbocation to secondary carbocation and the but2-ene becomes the major product. Although this is mixture, but2-ene becomes the major product. However, it looks like that but1-ene should be the major product, but in reality, but2-ene is major product. You will write this statement. But2-ene is the major product formed due to rearrangement. This is what your teacher and examiner will be looking for, rearrangement keyword, to give more stable secondary carbocation. This is another keyword, secondary carbocation. These cases you should remember specifically. These are type of exceptions. Questions appear from here very frequently. Next question. Ortho and para nitrophenols are more acidic than phenol. Draw the resonance structures of the corresponding phenoxide ions. This is a straightforward question because you know what structures are there. Just draw the structures. These structures you should already know. This is something we have talked about in resonance also in 11th grade. That resonance is triggered either by excess of electrons or negative charge, okay, or unsaturation. In this case, excess of electron and negative charge responsible So the resonance gets triggered from here. The excess charge here results in movement of electrons to this bond, and this double bond is formed. The moment double bond is formed, this carbon cannot have five bonds. So this bond actually breaks. When this bond breaks, you have both the electrons here. These electrons now move to next bond and these form a double bond here. When double bond is formed here, now this carbon cannot have five bonds because the hydrogen is there, which is not written here, five bonds. So this bond breaks. When this bond breaks, we have both the electrons here. These electrons move to next bond to form double bond. Now this carbon has five bonds. It means this double bond breaks. When this double bond breaks, we have electrons here, both the electrons. Then again, these two electrons move here, form the double bond here. The moment we have double bond here, now this electron cannot have five bonds. Again, this bond breaks, and the electrons are sent back to the oxygen. This bond breaks, we get oxygen. So here it will be single bond, and there won't be these two electrons. This is a misprint. So we will get six electrons back, negative charge back. The only difference between the initial one and last one will be that the double bonds in the benzene ring will change their positions. So double bond here was at right side, here it will be on left side. Otherwise it will be same. These are five configurations of phenoxide ion. Draw these. You will not only use it here, there will be indirect questions as well about stability, instability. Here we will be using these structures. So draw these structures and try to understand the mechanism. All the arrows you need to have very clearly defined arrows. One way to what students feel comfortable. However, I anyway suggest that you should understand instead of cramming it. But few students find it easier that first the arrows are here, then where they end from there, then where they end from there, then where they end from there. Arrows are just propagating, they are similar. Okay, why these are similar? In first case, electrons are transferred. In second case, bond is broken. Similarly here, now electrons are here, electrons transferred, bond broken. Then electrons transferred, bond broken. Again, electrons transferred, bond broken. So few students understand it like this and find it easier to draw the resonating structures. Now this is in case we have nitrophenol. So in case of para-nitrophenol, this will be the resonating structures. Now it is almost similar. The only point here is that there is resonance within NO2 also. There is resonance within NO2 also. So after we have done here that movement of electrons, bond broken, we from here we do movement of electrons, bond broken, then movement of electrons, bond broken in one arm where we have double bond in that arm. So resonance goes to oxygen and comes back to the benzene ring. But the concept is same. Electrons transferred, bond is broken. Electron transferred, bond is broken. To draw these structures, before I move forward, from here, very straightforward questions will be there. So if you are practicing it, if you are memorizing it, it means you are ensuring that you will get marks. One specific question appears that why um, the presence of NO2 group increases the stability of phenoxide ion. And the reason is because it increases the extent of resonance. There is resonance in this NO2 group as well. Earlier, the resonance was only in phenoxide ion. If NO2 group is attached, it increases the extent of resonance. That's why more stable. Now resonance structure of meta nitrophenoxide ion. Again the same thing, exactly same thing. Electron transferred, bond, then here again electron transferred, bond broken. Then back, electron transferred, bond broken. Now here slightly these arrows are not correct, so I'm correcting these on both at both places. Okay. When it is coming back, actually this arrow is not like this. When the bond is broken, it actually provides electrons here. Okay. And within the same step, the bond is formed here and this bond is broken because these electrons are here. So these two steps are combined. So understand it what I am saying. Okay. So you can think that first electrons are transferred here and then these electrons transfer here. They form the bond, which has been written in single step, one step. This bond transfer here. So that's why a bond is shown here. That this bond has transferred from here to here. So this combination of two steps, which you show as one step. Similarly here, when this bond is shown here, this bond is being transferred from here to here. That's why you see a bond here. Draw these structures and try to practice without looking onto the screen or without looking onto your book, notebook. Then you should think that you will be able to draw these structures in exam. So it can be observed that the presence of nitro groups increases the stability of phenoxide ion. This is what I told you, okay? Because it increases the extent of resonance. I'm going back. Ortho and para nitrophenols are more acidic than phenol. You need to provide the reason. Draw the resonance structures of corresponding phenoxide ions. So the question is actually why ortho and para nitrophenols are more acidic than phenol. It is because the phenoxide ion formed is more stable. So you have phenol, from phenol, in both cases phenoxide ion is formed. When phenoxide ion, you remember ONA, right? It is ionic compound. So phenoxide ion is formed. This is very much stable because it has resonance. But if we have NO2 here, then it will be rather more stable. Why? Because NO2 will have resonance. Whether it is at ortho position or para position, in both cases, it will have resonance. It will increase the extent of resonance. So that's why, because the phenoxide ion being formed is more stable, this reaction will be taking place more easily or will be more reactive. It means these nitrophenols, ortho or para, are more acidic. Why more acidic? Means they are losing hydrogen. This reaction is showing the acidic character of phenol or nitrophenol, whether ortho or para, because hydrogen is going away. So it means acidic character increases due to higher stability of the product. Next question. Write the equations involved in the following reactions. You remember Riemann-Tiemann reaction, Kolbe's reaction. So just you will unmute your mic. I will ask the question, and you need to unmute your mic and tell me the answer. Okay. Yes, Tuhina, tell me. In Riemann-Tiemann reaction, what is the reactant, what is the reagent, and what is the product? Tuhina, unmute your mic. Are you listening to me? Okay, so just mark the presence, everyone. Write present in chat box. I need to know how many of you are listening to me. Write present in chat box. Hmm. Okay, Tuhina. So I ask one, if you don't know, yes, Sneha, what reactants, what intermediate reagents, and what products related to Riemann-Tiemann reaction? Unmute your mic. I told you this is very common, very important question. Yes, I am getting answers from others. Okay. Yastika, Ashi, Preeta, Arohi have given answers in chat window. Yes. Tell me next, Armina. Riemann-Tiemann reaction. Reactants, what reagents are used and what products? Unmute your mic. I think I need to schedule a Viva. It gives me a feeling that it is now necessary to schedule a Viva. You are so shy to speak on mic. Shashwat, yes, but you need to mention for call-based reaction, you need to mention the second step as well. Okay, back, correct. Riemann-Tiemann reaction actually was the second one which I discussed. First, I discussed coal-based reaction in which salicylic acid was formed, and I said that in coal-based reaction, if you see first is you get it reacted with NaOH, it is only phenoxide ion. In second step, you get it reacted with carbon dioxide, okay, in acidic environment, which introduces carbon of COOH. So that was coal base. Riemann Tiemann I discussed after that, and I said in that case, salicylaldehyde is produced, and carbon is introduced in first step by CHCl3 along with NaOH, and second step is just acidic environment H plus, nothing else. You need to remember these. Okay, so Riemann Tiemann reaction, salicylaldehyde is formed. Okay, intermediate parts you may skip, but at least these parts are very important. You use phenol in first step, CSCl3 and aqueous NaOH actually introduce carbon. Second step, you get phenol group, OH group. Coal base reaction, first step, you get phenoxide ion, sodium phenoxide. And in second step, carbon dioxide introduces the carbon dioxide along with acidic environment. This is the reaction. First step is only NaOH, you get sodium phenoxide. And it is the second step. So this second step is actually combined. Okay, you don't need to write everything. If you write, that is good. If you can write the intermediates, very good. But if you are struggling, you can skip. So carbon dioxide and acidic environment actually introduce COH. Very important reactions, very important named reactions. Okay. Next is ethers. So this completes your alcohol and phenol part. Now the third part is about ethers. First is preparation, dehydration of alcohols. This is something, if you remember, we talked about. Just the difference of temperature. We talked about it in properties of alcohols. At 443 Kelvin with H2SO4, we get alkene, but at 413 with same H2SO4, we get ether. Okay. Now the point here is that we will always get symmetrical ether. What is symmetrical ether? Symmetrical means the alkyl groups will be same. C2H5, C2H5, because we are using same alcohol. Okay. Same alcohol. If we use different alcohols and we want, unsymmetrical ethers means these alkyl groups are different, then we should use those alcohols which have very different boiling points. Okay, so that's why the ethers produced have very different boiling points. We are able to separate those. Okay, otherwise this should be used for producing symmetrical ethers only. So the formation of ether is a nucleophilic bimolecular reaction, that is SN2, involving the attack of alcohol molecule on a protonated alcohol as indicated. I had here, so this is the mechanism which is asked. So it is good that you draw it right now and understand. And remember this statement. Attack of alcohol molecule on a protonated alcohol. This is the key feature of this mechanism. Alcohol molecule attacks on protonated alcohol. So first, alcohol with H plus, this is protonation. Okay, first step is protonation. H plus gets attached, and because H plus gets attached, this hydrogen has provided this oxygen has provided both of its electrons to hydrogen. That's why oxygen gets positive charge. Positive charge on oxygen, as we have seen in case of other mechanisms, is not stable. So because it is not stable, what happens that this bond, okay, sorry, this bond provides its electrons to this oxygen. Okay, how it provides? Because this alcohol molecule gets attached to this carbon. Now remember, it is not step by step. It does not happen one after the other. Everything happens at the same time. Understand what happens. There is a tendency only that this bond starts moving to oxygen. Okay, the electrons of this bond, they tend to move. I'm not saying they move actually. They tend to move to this oxygen from here. Okay. When these tend to move, then this carbon gets slightly positive charge because this carbon tends to lose the electrons, slightly positive charge. Because this carbon has slightly positive charge, so this oxygen with excess of electrons tends to get attached to this carbon, tends to attach to this carbon. Now, because these, and then it happens, these electrons are transferred to this one. This is now H2O. It has its own electrons. Now charge goes. So it separates as H2. And the remaining parts, that is this part and this part, they get attached from oxygen. This part comes here and this part comes here. With oxygen, it gets attached to this carbon. So these two get attached. The second step is slightly, I would say not, I won't say difficult, but slightly tricky to understand. But if you understand, that's all, nothing else. So the alcohol molecule, again, another alcohol molecule. So one molecule of alcohol gets protonated. Oxygen gets positive charge. Then on this protonated alcohol, another molecule of alcohol attacks on the carbon, which tends to get positive charge when this water molecule gets released and forms intermediate. This intermediate actually, because this oxygen has positive charge, now deprotonation takes place. The first step was protonation. Second step is attack by nucleophile. Third step is deprotonation. So in these mechanisms, usually you will see if protonation is taking place in first step, and last step deprotonation will take place to get that proton back. So from here, these two electrons are transferred to the oxygen. It forms ether, and this proton is released, and we get the proton back. Protonation, nucleophilic attack, deprotonation. It is important that you draw the mechanism exactly as it is shown here. It might be, instead of ethyl alcohol, it might be propyl alcohol, but the mechanism will be similar. It will be only the carbon which is attached to oxygen. On that carbon, it will get attached. So even if it is CH3, CH2, CH2, and this is CH3, CH2, CH2, these groups will change. These will become CH3, CH2, CH2. Mechanism will be similar. It is used to produce symmetrical ethers. Symmetrical ethers, I have told you, they have same alkyl groups around oxygen. Next is Williamson synthesis, and this is the most important method for preparation of ethers. Most important in terms of because most of the questions appear from here. Now see the mechanism and reaction first and understand why it is important. The specific feature, if you see here, and what is different here, that in previous case, we were getting symmetrical ethers. In this case, specifically, if you see, we get sodium alkoxide, means these are alkoxides, sodium alkoxide. We get reacted with the haloalkanes. Okay? So alkyl halides, you can say. And this is the feature here, which you will remember, that alkyl halide will be primary and the alkoxides will be having tertiary carbon. It is preferred only in this case. And why it will not happen if we have vice versa? For example, we have 3-degree alkyl halide and 1-degree alkoxide. What is the difference? Why it will not happen? That is something we will talk about later. First, understand the reaction. And you need to remember what I am saying. Alkoxide will have tertiary carbon. Halide will have primary carbon. This is something you must remember. Quite a few questions on this concept. Then you will get unsymmetrical ether. Here both the alkyl groups are different. Both the alkyl groups are different. So write it down first before I explain it further. Now coming to that point, better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution. Instead of substitution, elimination is preferred. And there is reason. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. This is the reason we will be talking about that. But first, understand these points and memorize these points. If you use tertiary alkyl halide, means this one, if you use tertiary, no ether will be formed. If this one is tertiary, no ether will be formed. If it is secondary, then a mixture of ether and alkenes will be formed. So that is anyway not required. If it is primary, only then ethers in good yield will be formed. In secondary, ethers might be formed. Tertiary ethers will not be formed at all. So for example, in the reaction of primary alkoxide with tertiary bromide, it will give you only alkene, 2-methyl propene, nothing else. So if it is opposite, 3-degree halide in Williamson synthesis, halide must be 1 degree. Memorize, repeat it in your mind again and again. 1 degree alkoxide, okay? Sodium methoxide, for example here. Then only alkene is opposite. It is because alkoxides are not only nucleophiles but strong bases as well. This is answer to these type of questions. So you must remember. The reason is alkoxides are not only nucleophiles, these are nucleophiles because these have electrons, but these are very good bases also. And what are bases? Bases are which can provide electrons very easily, which can lose electrons very easily. These actually can lose electrons very easily because these have ionic nature. Okay, so you might say that in CH3, CH2, OH also we have this oxygen having electrons here. But why it does not work as base? Because it is not in the form of ion, it is not willing to lose electron. It can, yes, attack by these electrons as nucleophile, but will not be willing to lose these electrons. Base means willing to lose electrons. To answer, you need to remember why, because alkoxides are not only nucleophiles, these are nucleophiles, but also very strong bases. So they react with alkyl halides, leading to elimination reactions in this case. Now you might say why it does not happen when it is the opposite is the case, that we have tertiary alkoxide and primary halide. For that, you need to recall the mechanism, how SN2 reaction works. SN2 reaction works, if you remember, that attack is from one side and the group leaves from the other side. It is inversion of the group, means there should be attack possible. Attack by nucleophile should be possible. So I'm just explaining first, if you recall that the mechanism, if you have bromine and you have CH3, mm, CH3, CH3, and nucleophile attacks from here. Is there any possibility it can attack? There is huge hindrance. Okay, huge hindrance. Nucleophile will not be able to attack. So it means elimination will prefer. Elimination will be preferred. Now, before that, I need to make it very clear that it is not that a particular type reaction will always take place. Only that reaction will take place which is easier to happen. So if elimination is easier, elimination will happen. If substitution is easier, substitution will happen. In this case, substitution will not be possible because nucleophile will not be able to attack on this carbon due to huge hindrance. Hence, elimination will take place. So for that, bromine will go away and hydrogen will go away, one hydrogen, and double bond will be formed. So that is the reason here. So they react with alkyl halides, leading to elimination reaction instead of nucleophilic reaction.